Good afternoon, everyone. So it is my pleasure to welcome you to this other appointment of the 40U40 lecture series on combustion. So today we have the pleasure to host Daniel Mira from the Barcelona Supercomputing Center in Spain. And we talk about towards high-fidelity combustion simulations. And let me introduce the speaker of today. So Daniel is the head of the Propulsion Technologies Group at the Computing Applications for Science and Engineering Department of the BSc in Barcelona. He received a bachelor degree in mechanical engineering from Universitat Politécnica de Valencia in 2008, and he has a PhD from Lancaster University in UK in 2012. He has been working at the Barcelona Supercomputing Center since 2013, and the research of Daniel is focused on developing advanced simulation methodologies for power and propulsion system using high-performance computing and data-driven models. Thanks again, Daniel, for having accepted our invitation, and I will give you now the floor for your presentation. Thanks.
Okay, thank you very much for the introduction, and thank you very much for the invitation. It's a pleasure to participate in this lecture series. So let me see if I can share the screen and everything works. Okay. Yeah, can you see the screen? Yeah, okay. Thank you. So, well, so let me just give you a short overview. As Alessandro said, I work at the Barcelona Supercomputing Center. We are located in the city of Barcelona in the northeast of Spain, and our institution hosts the supercomputer Mare Nostrum, which is one of the largest supercomputing facilities that we have in Europe. Currently, we are moving from our current system, Mare Nostrum 4, to the new pre-exascale system, which is Mare Nostrum 5, which is one of the three pre-exascale facilities that Europe has invested to support science and innovation. So this means that our research activities are very much aligned with the simulations of combustion systems, but trying to have peace with the development of the hardware architectures. So on our side, model, methods, and software are coupled together to take a benefit of the current generation of supercomputers. So with this, let me just go more into the presentation, what is bringing today here about high-fidelity combustion simulations. And just to give a little bit of motivation, I think it's not really necessary, but everyone knows in here that we are in the energy transition, and we are trying to adapt our future to be less dependent of fossil fuels with the aim to fight climate change. We all know that this is becoming an issue for our generation and the generations to come. And as has been pointed out and discussed on the TV by the politicians and by the main organisms, one of the major initiatives for decarbonizations is the use of electrification from renewable energy sources. But as you know, there are this becomes a viable solution, but this is not valid for all the application sectors. There are other sectors that are more difficult to decarbonize, for example, aviation or maritime transport, even industrial processes. These are sectors that have more difficulties to adapt to electrification. So if we look at these sectors more closely, we can see that in order to make them more efficient and carbon-free, we have really two main directions. The first one is to improve current combustion technologies. As you can see, engines and burners have been optimized and improved over the years. It has been demonstrated in our community, in conferences, and also by the things that we can buy in the shops. So this requires a substantial effort, and indeed this is a direction that we should take to improve our current systems. But even with radical new technologies, we can have big jumps towards reduction of even emissions or fuel consumption. But the impact is more on the long term. If we want to have impact on the short term, one alternative that is becoming quite relevant is to change the fuels. So we can retain the current combustion system, the combustion technology, but we replace the fossil fuels by alternative fuels that can be carbon neutral or cannot have carbon at all, like hydrogen. And with this, we are able to have a direct impact in these sectors in much shorter time. So in both strategies, combustion is at the central role, and it is the direction that is required for decarbonization. But if we want to understand and if we want to predict combustion, this is not an easy task, as you already might know. So if you look at, for example, some of the pictures that I put from here on the left, like some flames in furnaces, a hydrogen flame in an aeronautical combustor, or another flame of an oxy-fuel burner or a gas turbine burner. As you can see, this when we go to applications that are closer to industrial applications, then the characteristics of the flames and the burners become quite complex. And some of the aspects that are bringing this complexity are related to the existence of multiple injectors, complex geometries, interactions between these injectors and the walls and the environment of the system. Also, because the combustion process itself is very complex, is multi-phase, is multi-scale, and then you also need to have a description of the possible interactions that appear in all these physical phenomena. For all these reasons, it is a very, I mean, we can ask ourselves if we are able actually to perform simulations of real systems, and if we can, how expensive these simulations are going to be. So if we keep this direction, if we think about the combustion process itself, we see that combustion is a complex process that requires the injection of fuel. In case of liquid fuels, you have to inject a high pressure. Then the fuel is injected in the chamber. Then it requires atomization. So the liquid core of the fuel needs to be broken into ligaments. These ligaments need to form droplets. The droplets then evaporate, they mix with the air, and eventually combustion happens. So you need to account for all the physics associated to all these processes, and then the problem becomes quite complex, because you have for example, pollutants that are developed at certain scales. Then you have the heat release that is usually faster than the formation of certain pollutants. Then you need to account for turbulent chemistry interactions. So it is, at the end, we can say that combustion is a multi-scale and a multi-physics process, and therefore it requires advanced computational techniques in order to have proper characterizations of these systems with a high fidelity. And if you require complex simulations, this is usually coming with the use of high-performance computing that allows you to perform simulations in a feasible amount of time. So with these ideas in mind, it is important to understand that combustion methodologies should be developed aligned with the supercomputing and hardware architecture, so we can take advantage of the evolution of these systems and the computational power that they bring for our community. So if we are trying to understand how we can perform these simulations or how our methodologies should be based on, at the end, it's all really a matter of scales. If we think about spatial scales, for example, these are just, don't take it hard, but these are just some numbers that will give you some estimates. For example, we need to deal with systems that have a fuel injector, for example, with dimensions in the order of millimeters, when the combustion chamber is in the order of centimeters of meters. The length of the combustion chambers could be very long and could be very large in the order of meters, but then we also have aspects related to the flow scales, like the flame thickness or the integral length scale, that are associated to very small scales. So we need to deal with small scales that occur in very large volumes, which at the end introduces some complexities and some requirements of computational cost. So if we do a similar analysis about the temporal scales, at the end, it's about the same. We need to, if we are interested in the acoustics, then we need to be able to recover and describe the time scales required for the acoustics that could be larger than, for example, the formation of radicals and also emissions. So if we think about the requirements of the spatial scales, we are going to end up having a lot of cells in our computational domain, because we need to predict the distribution of the species and all these processes in these big computational domains. But considering the scales of the problem that we are solving, we're going to require a large number of small time steps if we want to solve all the processes in, let's say, in an explicit manner. So at the end, if we think about real problems, we can assume that doing DNS can be prohibitive, and these problems are more suitable to use runs. And now the question is, with this increase in computing power and computational capabilities, is it possible to push LES towards this type of applications? And indeed, if we want to go in this direction, we need high-performance computing, but this is not going to be enough. We need models. So if we go to LES, we need computational power, but also we need some models. So with this motivation, I just want to give you a little bit of orders of magnitude about how costly these simulations can be. For example, if we take as an example one of the simulations that we conducted about a hydrogen combustor that was experimentally characterized at the Technical University of Berlin, then in this for this flow condition, we perform an LES of a hydrogen air at atmospheric conditions. And then for a simulation of 30 milliseconds, considering 250 million cells, we require in the order of 100 hours using 6,400 CPUs. Okay, so if we want to do a simulation overnight, considering a simulation overnight, like I work in my office today, I prepare my model, and then before I go home, I submit my simulation, and I would like tomorrow morning when I get back to the office to look at the results. So if I want to do that with this simulation, I would require in the order of 60,000 CPUs to get for the same. So in this case, if you think about this, 60,000 CPUs is something that is currently available in the supercomputer. So they have even more cores than 60,000. But if we want to do something more realistic, just an increment in pressure in the order of 5 bars, it's a factor 5 in pressure, then for a similar simulation, we could more or less estimate, a rough estimate, would require in the order of 1 billion cells, and it would require in the order of 2 million CPUs, which is definitely not available in the current supercomputers across the world. So now the question is how we can make our simulations more efficient, or how we can deal, or how we can improve the software that we develop, so we can try to reduce the cost that is associated to this simulation. So let's try to talk a little bit about this. But if we want to understand how expensive numerical simulations are, this is really a very complex task, because it really depends on many things. The first one is whether you are going to use RANs, LES, and DNS. So depending on the technique that you use to solve the fluid problems, then the cost is going to change. So it also depends on other aspects. It depends on the discretization strategy that you use, so finite difference, finite volume, high order methods, for example. It also depends on the turbulent combustion model that you want to use for solving your problem. If you have a model. If you don't have a model, of course, it's going to be even more expensive. Then there are other aspects that are usually less discussed or less considered, which is about the algorithms and the parallelization that you have in your code in order to solve the problem. So if your code is serial, of course, you are going to take a certain time, but if your code is parallel, and then you can double the resources that you can use to compute the simulation, then the cost of the simulation will be reduced by half, or at least the time to solution will be reduced by half. So other aspects like how you implement the models, how you implement the algorithms play a fundamental role, but also whether the characteristics of the hardware where you run your simulations will also play a role, whether it is CPUs or whether it's GPUs, or these aspects, if it has accelerators, these all will really contribute whether your simulations will be feasible or not. So just to consider, in terms of degrees of freedom, when we go from RANs, LES, and DNS, what you can see is that the jump from RANs to LES is a very big jump, not only just in terms of degrees of freedom, but also in terms of the requirement of computing and steady simulation, but also there is a big jump when you go from LES to DNS. So for all these reasons, if you are interested or you need to conduct LES or DNS simulation, it is very important that your code makes an efficient use of the resources available in the supercomputer. So if we try to understand where this cost is coming from, because I've been saying a lot of things about physics, about computational requirements, but where is really, why these combustion simulations are so expensive? Where the problem comes from, really? So if we think about the conservation equations that we need to describe the flow or the problem under consideration, then we have to solve the equation for continuity, momentum, chemical species, and energy, and the system is closed by the equation of state. So at the end, more or less, you end up solving these equations that doesn't seem to be very problematic, but they become very, very problematic. And not only the Navier-Stokes are problematic, but also the equations related to the chemistry and combustion. In particular, for combustion simulations, the equation for the conservation of a species is usually the most demanding part, because mainly for two main reasons. The first one is because depending on the fuel and depending on the detail of the chemistry that you need for your problem, you might end up solving a very large number of transport equations. So, for example, if to describe the fuel oxidation, you need 20 species, for example, you will need to transport 20 equations that will go on top of momentum, continuity, and energy. And the other element or the other aspect that is important is that this equation for chemical species has a source term which is non-linear, and depending on the characteristics of the oxidation process, these chemical source terms can be very stiff, and it could require a very demanding or very costly calculations. So let's try to look at more closely this equation. So this is very fundamental, but I would like to just revise. So this equation at the end is composed by 4 terms. So we have the temporal term that is related to the time margin of the simulation. So how is the concentration, or in this case, the mass fraction of a species K evolving in time. Then we have another term that is related to the advection, how this species is moving with the flow. Then we have another term that is for diffusion, and another term for the source term, for the production and destruction of this particular species due to the chemical reactions. So this equation, of course, needs to satisfy certain properties that will introduce some requirements in your algorithms when you solve this equation. And then you will need to provide closures for the diffusion, because this term here, capital VK, I don't know if you see my mouse, but this term here is associated, is the diffusion velocity of the species K, and depending on the detail or the requirements in the description of the transport for a particular problem, this diffusion velocity or this diffusion term can become quite complex. So you can use simplified approaches based on the unity Lewis number or constant Lewis numbers. But if you want a very detailed transport model, accounting for this term can be also quite costly. And of course, the chemical source term, as I already introduced, that can be stiff, and you might require to use ordinary differential equation solvers for this. So considering this equation, and we can try to understand where the cost is coming from. So and what are the aspects that can introduce a penalty in the calculation for this equation. The first one is what we call the assembly of the partial differential equation. The assembly means basically the computation of the different terms, the advection, the diffusion, and the source term. So at the end, the number of degrees of freedom that you are going to have in your problem is the number of species that you have in your reaction mechanism times the number of cells that you have in your computational domain. So for each of these degrees of freedom, you will have to evaluate convection, diffusion, and source term. The other element that introduces cost and complexity in the calculation is the chemical source terms, as we already said. If it's stiff, then this could be require some iterations and some complex algorithms to extract the values. If it's non-stiff, then you can get away with more simple, explicit or semi-explicit methods. And finally, something that is also less discussed in the literature is what we call the load imbalance. So let me try to explain you a little bit about this, because this can become quite problematic in combustion simulations. For instance, if you have a computational domain like the one described here, these small cells are trying to represent the cells of the simulation, and these dashed lines are representing the subdomains. And then you can assume that you will have an MPI thread that will solve the problem in each of these subdomains. What you can see is that for the MPI threads that are solving this part of the subdomain, they don't have chemical reactions, because the chemical reactions are located around this red region here. So this is the region where you have chemical reactions. So the MPIs solving the problems here, they don't need to solve chemical reactions. So they don't have to solve this chemical source term, while the MPIs that are in this part here, they need to have a lot of cells that they need to solve for the chemical reaction, which at the end, this gives to solve problems. So in computational combustion, we usually analyze the performance of our parallel codes, checking what we call traces. So the trace is just nothing but a representation on how much work each of the MPI or the threads that are used in the simulation are doing. For instance, over these rows that are here, you can see the different threads. So thread 1, thread 2, thread 3, they are all here. And then what you can see here is the work that they are performing. So when there is black, it means that they are doing nothing, they are waiting, and when they have a color, it means they are doing some work. So what you can see here is that during the assembly, for example, when you compute convection and diffusion, everybody is working together, everybody is doing their job, but then, and they more or less take about the same time, okay? If you do the partition of the mesh in a proper way, then you can try to more or less ensure that all the MPIs will take about the same load. But when you go to the chemical integration, which is this part, CBOD is just the chemical solver that we use for this, you can see that there are some threads that are doing a lot of calculations. So the chemistry is maybe more stiff for this thermochemical state that what might be for this thermochemical state here. But there are some threads that they are doing no work at all. But at the end, until the slowest thread is finished, we cannot go to the next time step. So as you can see, the simulation could, or the computation could have finished somewhere here in the middle, but because there are some MPIs performing some work, we need to wait for them to continue, okay? So this can be a very problematic problem, especially in combustion when the chemical source term is very stiff, okay? So another problem associated to so the chemical source term is a troublemaker in combustion, in fact. So, and it not only bring a cost, but it means that when we want to go to LES and we need to filter this equation in space, then the problem is how are you going to perform the filtering of this term? And this is not a simple problem. And depending on how you filter this term or how you would like to have an equation for a chemistry that is based on filter quantities, then we end up in a quite wide scope of different turbulent combustion models. I have listed here by the acronyms. You can then find them in the literature. They will come up with these names very easily. So as you can see, there are plenty of turbulent combustion models that are in the literature trying to provide let's say an efficient method that we can either filter this term or we can either consider an equivalent equation that corresponds to the filter quantities, okay? But I like more, at least for the topic of this afternoon, to discuss in terms of turbulent combustion models from a computational cost perspective for models that are based on the Arrhenius law and computing the species and the chemical source terms. We call them we put them in the category of finite rate chemistry. And then on the other side, there are other methods that are based on tabulated chemistry, which try to reduce the computational cost by tabulating some terms that can be computed on the fly or pre-computed before the simulation starts. So for the presentation of today, I will just focus more on the tabulated chemistry method because they have good potential to deal with large-scale simulations and industrial applications because they are computationally very efficient. However, they also bring problems on how you can adapt these models to represent complex physics. So If we step into tabulated chemistry methods, then we can try, I will try to give a brief presentation of what these methods are about. And then, of course, you can dig more into the references that I put here or in the literature for additional details. But for example, considering a turbulent flame where you have your first gases here, you have your burn gases there. So there is a reacting layer that goes from unreacted to fully reacted mixture. And then if we assume that this flame length can be smaller than the Kolmogorov length scale, then we could also then assume that the turbulence cannot distort the flame structure in this case. And therefore, we can assume that the fluxes that go perpendicular to the normal of the reacting layer can be smaller or less significant than what's happening along the normal direction of the flame. We can actually assume that our turbulent flame can be composed by a composition of 1D laminar flames, as then you can get a representation as it was done in this nice picture from the paper from Professor Van Oygen about the flame-generated manifolds method, where your flame is actually, even though it's 2D in this case, or it could be 3D, it is locally one-dimensional, okay, along the normal isosurface of the flame front. Okay, so if we are make this representation, then the solution of the problem can be quite nice, because you can start from your full conservation equations that we presented before. And then if we consider a gas with NS number of species, then you can try to go from a situation where you will have to solve ns-1 equations to a situation where if we identify variables that can represent the space of solution, then if this number of variables is much smaller than the number of the species, then we can reduce the cost of the simulation, because we don't need to transport all the equations, but we just need to transport certain number of variables that are representing the composition space, okay? So this is usually considered in the frame of the FGM. We use the mixed fraction and a progress variable, okay? But you could have even more controlling variables, okay? So then we can go to a system of NS number of equations to a system where we have NC, or number of control variables, number of equations, and which is actually quite nice, okay? So, and how we build this model? So, well, if we consider this representation of these control variables, then the database or the manifold where the information is going to be stored can depend on the configuration that you use. Usually, for FGM, we have two main configurations. We either use the premix flame configuration, for example, that I believe that you are all familiar with. We have unburned conditions here, we have fully burned conditions there, and then we have this distribution of fuel, oxidizer, and temperature. So this is a 1D configuration, and we can try to represent the 3D flame by a composition of one-dimensional flames like the ones that are described here, okay? If we apply this, if we consider the one-dimensional premix flames along the flammability range as it is described here. So we have the lean limit, we have the rich limit, and then we generate one flamelet solution for each equivalent ratio. Then we can build a database based on premix flamelets very easily and apply this in our FGM method. Another topology that is used for the flamelet database is the counterflow diffusion flame, which has a different configuration. So you will have the oxidizer coming from this way, the fuel coming from this way, and then you will find a reacting front in the middle. And then what happens in this case is that when you vary the level of strain, which could be either the distance or the velocity, then you are defining different thermochemical states, okay? So in the case of diffusion flames, if we use a representation based on the mixed fraction, and in this case, a reference progress variable, we can see that we can go from more or less the equilibrium solution. By increasing the strain, we are getting these sort of profiles until we get to a point in the extinction is produced, okay? And then we can build a manifold based on the tabulation of all these flamelet solutions between the stable of the stable branch going from near the equilibrium up to the extinction point. So in general, when we apply this type of methods, we usually move from the strain to the scalar dissipation rate to have information based on the variables that are obtained in the computational domain, okay? So at the end, you can end up with very complex flamelet architectures for trying to predict more complex physics. For instance, we can include what I was representing here. This is a representation, in this case, the temperature versus the strain. And what you can see is that what we were showing before is just the tabulation of the stable branch here, and then until we get to the extinction point. And then one possibility to incorporate unsteady effects into the flamelet manifold is to reconstruct the unstable branch and tabulate based on the flamelets associated to the unstable branch. Another possibility is from the extinction point to define an extinguishing flamelet that can recover all the space. So at the end, whether you define your manifold space using premix flamelets or whether you define using diffusion flamelets, this is something that is going to affect your calculations, okay? And this is something that we're going to try to see now with some examples. So after you define the structure of the flamelet database that will have an impact on your calculations, then you also need to account for turbulent chemistry interactions. So in the context of tabulated chemistry methods, there are fundamentally three main possibilities. The first one is to do presumed PDF methods, basically to assume that the effect of the turbulence in the flow will into the source term and the tabulated quantities follows a certain distribution. Then you can get your laminar database and you can integrate it with this particular function. We usually use beta or delta functions. Another possibility is to artificially thicken the flame. Well, in this case, to thicken the progress variable equation, and then you can account for these turbulent chemistry interactions. And then the third method is the method of F-tackles that is based on filtering the flamelet solutions and recover the correct flame based on the filter size that you have in the mesh. So these are more or less the more conventional methods that are used. And in the context of this presentation, I will just focus on the presumed PDF, which is more widely spread and more, let's say, more conventional for practical applications. Okay, so just to get an idea of the workflow, so when we go to tabulate the chemistry methods, basically we first define the flamelet generation. So we define the configuration that we will generate the database. Then we construct a flamelet manifold. So we do the coordinate transformation from physical space to composition space. And then we consider some grid treatment with the filtering, presumed shape PDF, and then we couple this with the CFD. So this approach is quite interesting because at the end, by just transporting a reduced number of equations, you are able to recover all the properties that you need from the flame. You can have access to compositions of all the species, even radicals, reaction rates, and properties. So this method is quite interesting, and then you don't need to compute anything in runtime. So you just need to go to get access to the database and recover the properties that you need in runtime. However, the use of these methods to predict the unsteady and complex physics is quite it introduces some complexities. Okay, so some of the complexities, let me just mention, is how to deal with multi-regime phenomena. So what would happen in situations where you have a premix front that will be interacting with a diffusion flame, when you have stratification, when you have auto-ignition, for example. Then about pollutants, if you want to incorporate in your manifold a slow species with fast species, how you can accomplish this if you have a single progress variable, for example, how you can include detailed transport phenomena, for example, for hydrogen flames, or other issues more on how I can retrieve the information from my database faster. So these are areas of current with current activity in the community on how to improve or develop more tabulated chemistry methods that can incorporate all these physical phenomena. Okay, so for the presentation today, I will go now a bit fast with some examples. We will try to show you how these methodologies are used for certain problems of practical interest, and I will just touch a little bit, not too much in detail, how you can incorporate soot, for example, in the flamelet database, and you can apply this to turbulent flames, obtaining, let's say, a quite good, let's say, accuracy in the calculation while keeping reduced computational cost. Okay. So for the applications, I will focus mainly on these 4 applications. It's a hydrogen-enriched natural gas flame, is in a swill burner from DLR Stuttgart, then a spray flame, and then 2 shooting flames, the Sandia ISF flame and a DLR aero engine model combustor at pressurized conditions. Okay, so all the applications that we do, we use our code that is called ALIA. It's a multi-physics code that is developed in our department now for many years, and it has quite well interesting capabilities in terms of computational performance and also in terms of physics for not only for fluid mechanics but also for structural mechanics and nuclear applications and other type of electrochemistry and electromechanical models and all type of couple phenomena. So for the applications, I will use I will present now, I will use the flamelet method based on transporting mixed fraction variance, progress variable and progress variable variance, and including normalized enthalpy to account for heat loss. It's all in the context of LES, and our numerics are arbitrary order Runge-Kutta order 3 mainly, and low dissipation numerical schemes for the low Mach number, and also for the reactive scalar transport. The code is parallelized with MPI and OpenMP, and it has been instrumented also to couple with machine learning models. Okay, so for the Prekinsta, I will try to go a little bit quick now. So really the motivation for this case is that there were some experiments conducted at DLR, and then they tested the influence of hydrogen in natural gas and which exhibit different flame characteristics due to the addition of hydrogen. And we wanted to understand if these flamelet methods were able to predict the dynamics of the flames, and also to try to see how accurate this approach was on predicting this physics. Okay. So this is the computational domain here. So the air is coming from a plenum here, then it goes through the swirler, and then the fuel is injected directly in the swirler. It mixes with the air across this conical shaped region, and then enter into the computational domain. So I will just present here, there are several operating points we investigated, but I will focus today on the point 1, which is the non-reacting case, the case 2, that is pure natural gas, and the case 4, which is 50% hydrogen, 50% hydrogen on the natural gas. I will skip the results of the 40% hydrogen because it has a stable solution, and this brings quite a lot of complexities for the simulations. But all the details are available in these publications from Leo. So as you can see here, you can see the dynamics of the case with pure natural gas. What you can see is that the flame is fully detached from the cone, and it exhibits some oscillations. It's quite unsteady, it's unstable, and it features a precessing vortex core that was quite well predicted by the modeling approach with an error less than 7%. So you can see here the experiment, and the LES was able to predict this precessing vortex core. So the dynamics of the flame were quite well recovered by using tabulated chemistry, which means that we'll have a quite relevant reduction in computational cost. Then we compare the cases. This is the non-reacting case with the case with the pure natural gas and 50% hydrogen. And what we can see is that the flame, as the hydrogen is included, then the recirculation is widened, and then the comparison with the experiments is qualitatively well captured. Here you can see more quantitative assessment of the flow field by comparing the experiments with PIV with the numerical simulations. And what you can see, the agreement is fairly good for all the operating conditions. Okay, this is the case with the inner case, the natural gas, and the hydrogen. And here you can see this is more interesting, that this is usually where most differences usually come from, along the center line. And what you can see is that when you go from inert to reacting, the recirculation becomes stronger in this case. What you can see is that in this case, the flame is detached. And then, you create this recirculation. And then in the case with hydrogen, the flame is attached, and then the recirculation is lower, but also has a quite a longer recirculation zone. So you can see here, you already see that the dynamics between the case 2 and the case 4 are going to be quite different. So what you can see, this is what you can see here. So you can see the case with pure natural gas it forms this type of flame, which is a V shape. The case with 40% shows the flame that gets attached, and the case with 50%, the flame is actually fully attached. So the tabulated chemistry model was able to predict the transition from the M shape to B shape by the addition of hydrogen. Another interesting case is that we can use tabulated chemistry and also brings quite a lot of complexities is about spray flames. This case is a Cambridge spray burner from the Professor Mastorakos at the University of Cambridge. And this burner is characterized by a swirling air that is coming from here. So the air is coming from a plenum here and then goes to this swirler, and then it gets into the combustion chamber. In this case, the fuel is injected through a spray, is like a pressure atomizer. And here, and then the air is mixing with the fuel, and then the flame is formed. So in this case, this is a configuration that tries to mimic realistic gas turbine conditions, but in a more controlled environment, so measurements can be taken and then validation can be performed. One of the main characteristics and one of the limitations of the flamelet models is the ability to reproduce lift of lengths, which is associated usually to unsteady phenomena. So this experimental database has information about this and OH PLIF, and we can use this to assess the predictivity of the tabulated methods for this particular phenomena. As always, we consider in this case two different meshes, a coarse mesh and a fine mesh. With in this case is we have the resolution in the region of interest from 1 millimeter to 0.5 millimeters, and then what you can see here is more or less the dynamics of the flame. So you can see the location of the spray is here. So the fuel particles are interacting and crossing the flame front and are interacting with the layer. And then, well, you get all these dynamics that the flame that are shown here. I think it might be seen more clearly in these plots here. What you can see is, for example, by looking at the OH, how the flame tends to get detached from the black body here. And then this has certain dynamics that we try to evaluate. So first, of course, we look at in spray flames. You always need to start by comparing and by looking at the velocity of the particles and the diameter of the particles. We compare here different meshes, and the results are in quite a good agreement comparing with experiments for the velocities, particle velocities, outer mean diameters, and even fluctuations of the velocities. So in this region here, in the inner region of the spray, the results is quite acceptable. And then at the edge of the spray, the comparison is not that good, but because there are less droplets, this part is a little bit less relevant. But overall, the agreement was good. So here, I just brought this picture to show you that indeed in the tabulation of premix flamelets, we're able to recover fairly well the lift of length that happened in this flame. If you look at the coarse mesh, this is the PDF corresponding to the lift of length at the distance. And what you can see is that by refining the mesh, the simulations were able to recover the probability of finding, let's say, a lift of length of a certain distance. Okay, so now I will rapidly go into soot formation. So we were working over the last 4 years in an European project called Estimate about developing advanced soot models for large eddy simulations that do not include only the soot mass fraction, but they were also able to provide a particle size distribution. So it was a collaborative project, and it was quite interesting, and we developed different methodologies, experiments, reaction mechanisms, and it was quite successful in the sense of advancing the knowledge of soot formation and also creating models for LES. So in the context of the project, we work with two main concepts, the method of moments that was mainly addressed by the Technical University of Darmstadt, and we were working with Professor Van Oygen in the Technical University of Eindhoven in the context of the discrete sectional model. So in this case, we were developing a methodology, or we were evaluating a methodology to try to incorporate the SUT model in the FGM table. And basically, what was possible to obtain, and I will show you some results, is a methodology that couples the FGF chemistry with the discrete sectional method, and we tabulate the source terms related to the SUT into the database. So in the end, both chemistry and SUT only require the use of transport equations, but not computation of source terms were required in the CFD. All the calculation of the source terms were computed directly in the flamelets, and then during runtime, these properties were recovered. So for this, we look at the Sandia ISF flame. This was conducted mainly by a PhD student at the time, Abhijit Kalbur from Eindhoven, who did an excellent job on developing and applying this model to different cases. So in this case, this is a very well-known Sandia ISF flame. Is a jet flame with a pilot that is coming from the surrounding, and then the hot gases from the pilot interact with the fuel, and then well, it develops this jet flame that you can see here that is has a lot of soot. So in this case, you can see some of the instantaneous plot of the shape of the flame. In general, the agreement with the experiments about the flame was good. You can look at more details about this in the publication. And here you can see the dynamics of the flame. And then you could see exactly where the soot is formed. The soot starts forming mainly in the region. This is the region with highest soot concentration, and then this is the developed and transported and further oxidized downstream. So here we compare the intermittency, comparing the FGM with a method that computes the source terms in runtime with a method that tabulates the sources in runtime. What you can see is that the case with computed source terms is more accurate in this case at predicting the starting of the formation of the soot, but then in the region where the soot exists, then it was more or less the two methods are able to more or less behave in a similar way. So here you can see conditional means for the volume fraction over scatter plots between the computed source term and the tabulated source term approach. What you can see is that the tabulated approach is able to recover fairly well the characteristics of the case with computed source terms. And then here you can see a final validation in terms of the mean soot volume fraction and at different positions of the flame. And here you can see the general plot of the soot across the center line. What you can see, I mean, the first time that you see these things, you see, oh, the correlation is not very good. Indeed, it's not very good, but it is more or less what computational models are able to predict in this case. So I would say this is more or less state-of-the-art results for this flame. And the interesting thing is that with this tabulated approach, we are able to reduce by a factor 7 the cost of the calculation, considering or obtaining more or less similar results. With an effort to further improve and reduce the cost of soot formation with tabulated chemistry, a collaboration with Professor Van Oygen and Abhijit bring us to the idea that if we have all the soot already included in the flamelet, would it be possible to do some clustering of the sections so we can avoid transporting all the sections and recovering the source terms for each of the sections individually. So in this case, the idea was that instead of transporting 40, 50, or 60 sections, then you can cluster these sections, and then you are only transporting the cluster sections. So you can have a reduction in the number of equations that you need to transport by a factor 10, and because the distribution of soot is already given from the flamelet, then during runtime you can recover the soot source terms, and you can recover the particle size distributions. Okay, so with this idea, we were able to reduce the computational cost by a factor 3 or 4 compared to the method only tabulating the source terms but transporting all the species. And then in this compact approach, FGM cluster DSM, we are able to solve turbulent combustion simulations, including 3-4 equations for the FGM and 4-5 equations for the soot, which brings and reduces the computational cost of the simulations by a factor of more than 10. So we applied this methodology to another flame from the ISF workshop, but this is a DLR ethylene flame that mimics the behavior of an aero engine combustor. We perform this calculation in collaboration with the CMT from the Polytechnic of Valencia. This activity and this project was conducted by Ivan as a part of his PhD thesis. And in this case, we were trying to apply this advanced soot model to solve this problem here. So the burner is characterized by an air inlet that is coming from here. It goes from the plenum, it goes to the swirler. There is 2 swirlers here, and then the fuel is injected from an orifice in the middle. In this case, we use the tabulation of diffusion flamelets, including the soot, and we look at 2 operating conditions at 3 bar. One that contains dilution air, that basically is when the flame is established, they introduce some air here, mimicking the RQL-like technology, by doing some sort of quenching of the flame and the flow, and then the other case in which no dilution air is injected. Okay. So in this case, you can see this is the velocity field. Of course, we start by validating the flow. This is the velocity field across the center line, and also at different axial locations. You can see here is this is the dilution jet coming from the side. So this is why you have a strong velocity coming from here. And then doing something similar from the temperature, we found also the temperature was in good agreement with experiments, so which validated the combustion approach based on FGM for this problem. So we use diffusion flamelets in this, and these results really confirm that this approach was suitable for this problem. So here, more interestingly, we can see where the soot is formed. So here you can see on the left the precursors from soot, in this case pyrene, where the pyrene is formed in this part. And more interestingly, you can see the soot volume fraction, where the soot is mainly formed in this part and then is transported downstream. What you can see is that the soot is mainly produced based on acetylene in this case, and then is the term that really dominates the formation of soot is the surface growth. Here we look at different soot subprocesses for the formation of soot, and you can see you will have a lot of details of the analysis of this flame in the literature. So I just wanted to point at you this. So with this brings me to the conclusion. So if we are interested, or we are targeting simulations for industrial applications, it is important to take into account the physical models, the numerical methods, and the high-performance computing algorithms, and the hardware where we run our simulations. We still have many challenges ahead related mainly to the decarbonization. with new fuels, with emissions, and if we want to develop methodologies for this, we need to account for some challenges related to multi-regime or preferential diffusion. That these are topics I didn't cover today because of the lack of time. And to just conclude that it is important when you do LES and DNS to not let your code to become old, and you need always to push the new techniques and develop the code that can run on the new architectures, because there is always a lot of potential and a lot of computational power coming from these systems. With this, of course, I have a lot of acknowledgement. This is the work conducted by many people, and with this, I would like to thank you very much for the opportunity, and I'm happy to take questions.
Thank you very much for this very nice talk and comprehensive. There is time for questions from the audience. Anyone has a question, please raise your hand so that we can give you the word. Okay, I see that Salvo has a question. Salvatore.
Yes, thank you, Daniel, for this insightful presentation. I have a question related to the computational efficiencies of this method. If you think that eventually finite rate chemistry approaches will bring the necessary accuracy while not being so much more computationally expensive in the future compared to flamelet, the flamelet modeling framework that you have shown. What do you think will be the if there will be a convergence, like towards more accuracy, and what we have to pay the price of more computational cost, or the other way around, or there will be a compromise?
Yeah, okay, thank you. Very interesting question. In fact, I think we have now, and I didn't cover it because I tried to cover too many things, as you can see, and I had to run at the end. So we have game changers now at different levels. We have machine learning, we have GPUs, and what has been efficient in the past, limited in terms of predictivity for certain applications, like tabulated chemistry methods that initially were developed for purely premixed flames or purely diffusion flames. The researchers have been extending the applicability of these methods to partially premixed flames, stratified flames, multi-regime flames. But still, when you use these methods in conditions that you don't know, for example, then it has certain element of risk that you put in your calculations, because you don't know what's happening inside the combustion chamber, and you need to make a lot of assumptions before you start when you use this type of methods. So I think using finite rate based chemistry methods is really a very important direction, especially now that we have more computing power available, so you could afford it basically, and you don't need to worry too much about what is the real regime of combustion in the problem, so you can go straight away with this. And this, despite that the computational cost increases, now you have mechanisms to accelerate the calculations, like GPU calculations. What you can do in CPU, you can do much faster in GPUs. The chemistry, which is really one of the problems that we have when we run this type of simulations, it's a kind of a calculation that is well suited for GPUs. So it is really, this can make a real impact. And of course, if by the use of machine learning, we can develop solvers that can be more robust and faster. I know there are many in in the community, and I think you are also working on this. I think this is really a very reliable way to go. It would be more expensive than doing flamelets, but it could be more accurate and more, let's say, more safe when you don't know what you are going to find out in the problem.
Thank you.
Thank you, Salvatore. I don't know if there are other questions from the audience. I was actually wondering, I mean, I wanted to have your comment. I think it's interesting that you give your opinion on this to the people online. How do you see the role of DNS or high-fidelity simulations in general in terms of the possibility of developing or validating or pushing new model development, as well as, you know, I mean, from a perspective of developing new physical models, but also from a more data-driven perspective? How do you see this going in the next few years?
Well, I think this is really, this is really the direction. In the LES, there are models. So there are many assumptions that are based on having access to data that doesn't have those assumptions. So I think again, I just insist on the same. So there is more computing power available, but exponential growth of computing power over the years. And DNS is really the main, they will benefit the most from all the numerical techniques. The problem, fundamentally, the problem that I see with DNS is that the codes that are generally used for direct numerical simulations are legacy codes that do not really take advantage of all the parallelism available in the supercomputers. So I think these codes are very reliable, they are very good, but still they are based on old hardware. They are optimized for old hardware architectures, and therefore as soon as these DNS codes can shift to, for example, GPUs, then let's say what DNS codes will be capable of doing in a few years, it will be much more than what we have now. So we can try to approach in this project that we just ended in the Center of Excellence in Combustion. For first time, we saw the simulation of a shooting flame by Christos Frousakis and Ananias Tomboulides, a DNS of a shooting flame in an aero engine like a combustor. So DNS is really trying to push into the conditions where LES has been used. LES needs to go to more large scale. I mean, the challenge is to go to more large scale, but this is really a clear fact that DNS will be approaching more industrial conditions.
Thank you, Daniel. Thank you very much. If there are no other questions, we can close the meeting here, and I take the opportunity to thank you again.
Thank you.
And,
thank you very much.
I wish everyone a nice weekend, and I give you, I mean, and we meet for the next event, which will be, I don't know, Salvatore, tell me. In a couple of weeks or next week?
Yeah, in a couple of weeks.
Okay.
Yeah.
Thank you very much. Bye-bye.
Thank you for accepting our invitation.
Thank you very much.
Bye, everyone.
Thank you.
Have a
Bye-bye.
nice weekend.
Bye-bye.